An asynchronous motor, also known as an induction motor, operates based on electromagnetic induction. Today, I will explain you. The principle of electric motors, which I never understood until I graduated, turned out to be so simple. This is a metal bar that can be rotated. If a magnet is placed close to the bar will rotate in the direction of the magnet, and when the magnet moves, the bar will move with it. Now we replace the metal rod with an iron disc and replace the bar magnet with a U-shaped magnet. When we move the magnet, the disc will follow. If we keep the magnet circling the disc will follow, and the disc will also rotate. You might think that it's the magnet's attraction that causes the disc to follow, but the truth is much more complicated than that. Let's replace the ferrous disc with an aluminum disc, which is non-ferromagnetic, and when we move the magnet, the disc rotates just the same. So why is that? The magnetic field of the U-shaped magnet flows from the N pole to the S pole, and when the magnet moves due to the cutting of the magnetic inductance, according to the principle of electromagnetic induction, eddy currents will be generated on the iron disc. Through the right-hand rule can easily know that the direction of the induced current points to the center of the disc. In which direction does the disc rotate? It is necessary to use the left-hand rule. The index finger points to the direction of the magnetic field. The middle finger points to the direction of the current. The direction of the thumb will produce a force. It is this force to make the disc rotate. It should be noted that the speed of the magnet is not the same as the speed of the disc. If the same electromagnetic induction will not occur, the disc will not rotate itself. Next, we continue to improve the device by replacing the disc with an iron cylinder and the U-shaped magnet with two bar magnets. When we rotate the magnets, the cylinder will rotate with them. And let's look at the force on the cylinder. The magnetic field flows from the N pole to the S pole, and since the magnet is moving downward, the relative cylinder is moving upward. By the right-hand rule, it follows that the current flows in this direction. Again, by the left-hand rule, you can tell that the force on the cylinder is facing down. The same principle applies to the other side, yielding that the force is directed upwards, and eventually the cylinder will be able to rotate along with the magnet. So, can you make a cylinder turn without turning the magnet? Let's start with an interesting little experiment. In this experiment, when the direction of the current is constantly changing, the direction of the magnetic field is also constantly changing. According to this principle, we can put several coils around the cylinder, and when we keep changing the direction of the current, the magnetic field of the coils will keep changing, which forms a rotating magnetic field. As before, the force generated by the rotating magnetic field will be able to push the cylinder to rotate, which is actually the underlying principle of the asynchronous motor. Let's take a look at how a three-phase asynchronous motor works in reality. First of all, let's understand what three-phase alternating current is. When rotating the magnet around the coil, the change of the magnetic field will make the coil produce alternating current. The waveform of the current is like this, which is unidirectional alternating current. Three coils will be placed at an interval of 120 degrees, and then rotate the magnet. The waveform of the current is like this, which is three-phase alternating current. The three-phase asynchronous motor is connected to three-phase alternating current. The motor is mainly divided into rotor and stator, and the rotor is mainly composed of winding coils. First, the coil enters from the A port, then comes out in the opposite direction from the A port directly opposite, then enters from the B port at 120-degree intervals, then comes out in the opposite direction from the B port, and then the same operation is done to connect the coil into the C port at 120 degrees. And finally, the wires coming back in the opposite direction are connected together. The other three wires are connected to a three-way alternating current, and according to Ampere's law, when the current passes through the A coil, it produces a magnetic field, the direction of which is clockwise. The coil opposite the other end of the A coil also generates a magnetic field, which is counterclockwise. B and C do the same, and you can visualize this change better with this diagram. When the green coil is energized with alternating current, The direction of the magnetic field in the green coil changes in the opposite direction as the current continues to change, regardless of whether the coil is red or blue. When all three coils are energized, this creates two separate magnetic fields. As the alternating current continues to change, the magnetic field changes with it, creating a rotating magnetic field. With a rotating magnetic field, we can build an electric motor. This is a simplified squirrel cage motor rotor. By placing the rotor directly into the stator, the rotor is able to turn quickly under the action of the rotating magnetic field. This is just a simple motor made up of windings. There are more complex windings, but ultimately, they are all designed to create a rotating magnetic field. Asynchronous motors are used in a large number of applications in various industrial and agricultural production due to their simplicity, reliability, and ease of installation. Hope you understand now how asynchronous motor works. Thanks for watching. Like, comment, share, and subscribe.